Hello and thank you everyone for attending today's webinar, Thinking Outside the Circle, Applied Tribology, a Key to Improved System Performance, brought to you by Design World Magazine and GGB. We'd like to thank our presenters, Andreas Epli and Marco Enger, for being here today. I'm Mike Santora, Associate Editor for Design World Magazine, and I'll be your moderator. Just a few housekeeping details before we get started. You will see several boxes on your desktop, all of which can be moved around to suit your preferences. Initially, the Q&A box is at the lower left. This is where you will enter your questions for the Q&A session. Another box to note is the additional resources, initially at the lower right-hand corner of your desktop. These resources are for your information needs. We also have a tweet box right on the desktop, so feel free to tweet any interesting points right from there. And there is a list of hashtags for you to use as well. Marco Enger has more than 10 years of experience in tribology, tribometry, and all other related subtopics. In 2014, he became the Senior Tribologist at GGB and is responsible for all fundamental research works related to tribology. Before he joined GGB, he was working for the Competence Center of Tribology at Mannheim University, and he holds a PhD in mechanical engineering. Andreas Epli has over 10 years of experience in solving customer needs regarding demanding bearing applications. For the last year, Andreas has focused on the engineered plastics and the growth of the product line. Andreas is the Business Development Specialist for the EP range of GGB. And so, without further ado, here's Andreas Epli.
Thank you very much. So today's slides are about thinking outside the circle. Applied tribology, a key to improve system performance. But in the next slides, I want to quickly give you an introduction of GGB, what we can offer, and to whom we belong. GGB is proud to be a part of EnPro Industries. EnPro Industries is a global manufacturer of critical safety and high-performance products used in some of the most extreme environments. EnPro Industries operates R&D and manufacturing facilities around the globe and develop new innovative materials and technologies and support diverse engineering needs. On the right side, you see the companies which belong to EnPro Industries, like GGB, Garlock, Stemco, Fairbank Morse, Technetics, CPI, and GBT. Who is GGB? GGB has more than 115 years of experience in providing solutions to reduce friction, optimize product design through innovative plain bearing technologies. GGB can offer comprehensive selections of products to meet the world's most demanding surface engineering needs. We manufacture metal polymer, engineered plastics, fiber reinforced composite, metal and bimetal bearings, along with a range of supporting assemblies like bushing blocks and truss plates. Today, GGB extends its wealth of experience and history to lead polymer coatings into the field of tribology. The advantage of working with GGB is that we are your complete tribological service provider for the following industries, like aerospace, automotive, industrial, agriculture, construction, oil and gas, energy, fuel, fluid power, primary metal, recreation, solar, and packaging. Our comprehensive approach to understanding the complex science of interacting surfaces represents GGB's evolution from a parts supplier to a global tribological consultant. We proudly provide both manufactured components and engineering expertise to help our customers with their unique needs to create better surface engineering solutions. Our comprehensive understanding of tribology allows us to apply our expertise to any surface regardless of shape and material. With this being said, I want to hand it over to my colleague, Marco Enger.
So thank you, Andreas, for the introduction. So before we get started, I also thank everyone for joining this webinar. So today's presentation is part of GGB's Tribology University, or just in short, GGB's Tribou. The idea of Tribou is to share knowledge around tribology in all related subtopics. The topics normally cover the basic theory about tribology. Other topics have the focus on applied tribology and how this can be used to improve the performance of tribological contacts and thus the performance of mechanically engineered aggregates. So today's presentation is of the second nature, but don't be afraid, I will do a short introduction into tribology before we get started with the applied tribology topic. So when engineers are faced with mechanical design challenges, there is no right or wrong way to approach it. Some methods, however, we think are definitely smarter than others. For long-term trouble-free operation of an aggregate, it is essential to consider all relationships already in the design process. So this is important because only when everything fits and operates well together, the aggregates has a good efficiency and an optimal life cycle. So most engineers typically follow the process or approach they learned in the classroom of the university. Bearing contacts are a typical example of the standard design process, which is taught on the university. So bearings are typically selected when the engineer needs to insert one into their design. So they are often one of the last components of the design. So the engineer will consider the bearing type, the size, the speeds, and the loads. It sounds simple, but it is not, because one important aspect was not considered, which is tribology. We think that the optimal approach is to include also tribological aspects and factor them into the design at the outset of the design. Such an approach helps to improve the efficiency and the long life of the whole design. I'm pretty sure you have been asking yourself for a while why there is a cheeseburger on that slide. So what has it to do with complex aggregates and even with tribology? A burger sounds simple, but it isn't. It can be very complex. So the burger only tastes delicious when all the ingredients harmonize well together and when everything is cooked perfectly. This requires a huge amount of pre-work to find out what fits and how it needs to be cooked. So that's the reason for the analogy for tribological contacts. So let's start with some basic theory about tribology. So the first important thing is to understand what's behind the science of tribology. So the best way is that we take a look on the definitions of the term tribology. So the first definition is the easiest. So tribology is the science of friction, wear, and lubrication. The most common definition is the science of contacting surface in relative motion in all related topics and techniques. Another definition which I really like is that tribology is a multidisciplinary science in which advances are made by collaborative efforts of diverse scientific fields. So tribology is often accompanied with mechanical engineering, manufacturing, material science, medicine, chemistry, and physics, and we do have many more. This sounds very complex, but I will try to give you a brief overview of the main ideas behind tribology and how we can use that to improve the system. The interesting thing about tribology is that we can find it nearly everywhere. So during the next slide, I will introduce a few Tribo contacts found in many daily routines we have. And I'm pretty sure you will be surprised how many contacts you can identify after seeing that slide. As already stated, this slide covers typical tribological contacts in our daily routines. So to identify the contact, you just have to remember the definition of tribology, which is the science of two contacting surfaces in relative motion. So waking up in the morning and open a door within your flat or house is accompanied with the movement of a tribological contact. In this case, the tribological contact is the door hinge. Using the car to drive to work is also accompanied with tribology. So a car is a very complex vehicle containing many tribological contacts, and one very well-known contact is between the tire and the road. The human body also contains many tribological contacts, so each joint in the body of a human is a tribological contact. And braking systems for bicycles or cars are also very important tribological contacts. Walking or ice skiing is also a nice phenomena of tribology. So walking or running would be impossible without friction. Ice skiing would not work when the friction would be too high. So the last contact I would like to mention on this slide is directly from the nature. And this contact is the snail and the leaf contact. So the interesting thing about the snail is that it produces its own lubrication to reduce the friction between leaves and their bodies. So the snail slime is nothing else as a lubricant. So after seeing that slide, so I'm pretty sure now you can identify many other tribological contacts, also the tribological contacts in your applications. So throughout previous slides, we already used some important terms in tribology. So on this slide, I would like to explain them in more details. So let's start with the term wear. So wear is defined as the damage to a solid surface, normally involving material loss. And this happens throughout the relative motion of both contacting surfaces and maybe with another substance. We also use the expression friction. The definition of friction is the following. So the friction is the tangential force resisting the relative motion of two surfaces or bodies in contact. And tribology, we already explained that in details. When we discuss tribological contacts, we always discuss a tribological system. So on this slide, I would like to lead you through a typical dry-running bearing shaft system with all related impact factors. So let's start with the system structure. The term system structure is used to describe all substantial elements of a tribological system. The typical contact configuration for a bearing contact is here a hard and soft pairing. This means that one surface is normally softer compared to the other surface. And this is based on design requirements. So the soft surface is normally the bearing material. And this is because replacing a one bearing is normally the cheaper solution compared to a whole shaft replacement. The other aspect is that we use softer materials is that normally these bearing materials work better in dry running contacts when they work against a harder opposing surface. For the bearing materials, we can find a vast variety of different materials. A typically used material concept is the metal polymer composite. We can also find polymer composites in such tribological contacts. Coatings are also a great material family to lubricate tribological contacts. And other materials like fiber reinforced materials are also used for these dry running contacts. The second surface involved is the opposing or counter surface, or just simple the shaft surface. The property profile of the shaft can be rather broad. So we can find different materials like polymers, hard and soft metals. We can also have some coatings. So each of these materials has its own physical and chemical property profile that needs to be considered when designing a tribological contact. So beside the material, the topography of the counterface plays also an important role in tribology. So the term topography is maybe a new term for some people in the audience. Topography is just the scientific expression for surface irregularities. So each machined surface has its own unique topography character. Throughout the presentation, I will go a bit deeper in surfaces, and I will explain a bit more about surfaces. The last element involved is the environment. And I think you might miss some elements, and this is the lubricant, which would be the fourth element. But today we have to focus on dry running contact, so we exclude the lubricant for this presentation. The Tribou structure is stressed with the operational inputs. You see them on the left side. Another term for the operational input values is the collective stress. The collective stress encompasses the motion type, which is normally sliding for a bearing contact. For each application, we can find a broad spectrum of different loads and speeds. So the loads can reach very high levels. We can reach 100 MPa and above. Speed range can also be rather demanding. So we have some applications that goes up to 4 meters per second. A high combination of high loads and high speeds is seldom. And when it occurs, it normally is of short duration. A constant operation at high conditions normally destroys the contact due to overheating. The temperature range of such an application can also be manifold. So we have temperature range from cryogenic to high temperature applications. On the right side of this slide, we see the outputs of the tribological system. So on the one hand, we have the functional outputs, which is for bearing contact, a bearing and guiding of other parts. And the interactions among the elements of a Tribou structure leads to the so-called loss outputs. And the loss outputs are dissipation, which is friction, and the material loss called wear. That said, I think it's clear now that friction and wear aren't intrinsic material properties, they are system properties. As mentioned in one of the introduction slides, today's topic is applied tribology and how this can improve performance. We will be looking into the impact of the counterface topography on wear performance of bearing materials and how this impacts the bearing life and thus the application. Before we do that, I need to share some information about surfaces. At the first glance, the counterface is a surface which attacks the bearing material during the relative motion. In reality, we never find optimal surfaces. What does this mean? Based on an engineering perspective, we always face technical surfaces in real applications. So if we discuss the impact of metallic counterfaces on friction and wear, we discuss the impact of metallic technical surfaces. The main purpose of technical surfaces is the geometrical limitation of technical components. One crucial aspect of metallic surfaces is their multi-layer architecture. You see that multi-layer architecture on the schematic illustration on the right side of that slide. So this multi-layer structure includes the bulk material, the deformed materials through machining processes. We can find for metals, and we do have some absorption layers on top of that. Other treatment processes like coating add an additional layer on top of that. Each single layer exhibits its unique chemical and physical property profile. In addition to that, the topography is also an essential characteristic of surfaces. We often distinguish the topography in two ways. So we can say that there are some surfaces which has an isotropic and anisotropic characteristic. What does this mean? So isotropic means that the topography has no orientation. We can also say it has a random structure, or we can say it's equal in each direction. For an anisotropic surface, we have exactly the opposite. So their roughness peaks and valleys have a preferred direction. So on the right side, we see typical images of such topographies. They represent typical examples of an isotropic and anisotropic surface. They were generated using two different machining processes. So on the right side, we see a lab surface, and here we see the typical isotropic character. So we see that the same in each direction. So we don't have any preferred orientation of the topography. On the left side, we see the grinding, which generates a typical oriented structure, which is anisotropic. So far, we already learned that surfaces have own physical and chemical nature. We also know that surfaces also exhibit surface irregularities. So what happens when such surfaces contact each other? From a macro perspective, it looks as always. On this sample, we see a steel ball on a flat steel surface, and it seems to be an ideal contact. The microscopic view, however, shows that the surfaces only touch each other in those areas where we have these protruding surface irregularities. We tribologists call the sum of all these small areas the real contact area of a tribological contact. And tribology occurs in those small areas. The physical and chemical processes responsible for friction and wear are known as friction and wear mechanisms. As already stated, they occur at the microscale level of two contacting surfaces, and in those areas where we have the contact of surface irregularities. In tribology, we distinguish 4 main friction and 4 main wear mechanisms. So the friction mechanisms are adhesion, plastic deformation, plowing, elastic hysteresis, and damping. The adhesive friction component is a result of the formation and destruction of adhesive bonds within the real contact area. The 3 other mechanisms are based on a deforming interaction of asperities. So this brings us to the double nature of friction, and we can say, or we can simplifying it, that the friction is a sum of an adhesive component in combination with a deforming component of friction. So the wear mechanisms on the right side are adhesion, abrasion, fatigue, and tribochemical reactions. So the typical wear patterns are provided on the images below. So cracks are typical wear patterns for fatigue and often a result of a repeating stressing of the surface. Abrasion often leads to grooves and scratches because the harder asperity penetrates into the softer surface and normally furrow it throughout the relative motion. Adhesion often causes seizure and material transfer because of the formation and destruction of adhesive bonds. Chemical reactions can lead to particles which can also act as an abrasive in the tribological contact. So if we change anything in the tribological, or if we change something in the tribological system, this could be a change of the tribostructure, it could be a change of the collective stress. This will change the acting mechanism in the tribological contact, and thus will lead to a change of the performance of the whole system. Today, we will be investigating, or we will be looking at the impact of the counterface topography on the performance of bearing materials. Due to the vast variety of anti-friction materials, we decided to show you the impact of 2 typically used materials in bearing applications. So on the one side, we have the metal polymer composite. This material is a heterogeneous material. It has a multi-layer architecture. So starting with the metal backing for high mechanical strength, we have a porous cinder structure which provides 2 things. It has a high wear resistance, and at the same time, it's a mechanical interlocking system for the slide active bearing liner. And the bearing liner is normally composed of PDFE plus other fillers. One important feature of this material is that it generates a protective transfer film on the counterface, which then protects the bearing material from further damage of the counterface. By the counterface. The second material we investigated is a typical polymer compound. It consists of a thermoplastic polymer matrix. This this matrix material was slight modified using PDFE particles. The microsection shows you that the PDFE particles are homogeneously distributed within the thermoplastic matrix. And we know that this material also can form a pretty stable transfer film on the counterface. So during the last slide, I mentioned the word transfer film. And in the context of that expression, I used the term protective. So transfer films are rather important for the sliding performance of a dry running contact. And on this slide, I would like to explain you a bit more about transfer films. So most polymers and composite surfaces are worn by a harder counterface when we use them in tribotechnical systems. The inevitable wear of these materials when sliding against the harder counterface generates debris. The wear debris can escape from the tribo contact, but normally we hope that it stays in the tribological contact and hopefully deposit to the opposing surface. And then when the wear debris sticks, it can form a transfer film which protects the bearing surface from further damage by the attacking counterface by reducing its wear actions. So almost all tribologically optimized bearing materials exhibit the feature to establish a transfer film when sliding against the harder counterface. The transfer film is a very thin polymer or polymer metal layer on the counterface. Its thickness is approximately 1,000 times thinner compared to human hair. This relation is given on the right side. So the big circle represents the diameter of a human hair. The small dot underneath shows the thickness of a typical transfer film. It looks like a pixel error, so don't worry, nothing wrong with your PC. That is the thickness of a transfer film. Tribological testing is often indispensable when investigating interactions among elements of a tribological system. So we used wear experiments to describe the impact of the counterface topography on the performance of previously described. And we used a flat-on-flat test configuration, and this was realized through a pin-on-disk setup. The image on the left side shows you a schematic illustration of such a test setup. In this test, a small test sample pin is pushed against a flat rotating disc. In our configuration, the pin is the bearing material, and the steel disc was made of hardened 42 chromolybdene 4 steel. This steel disc had different topographies, and the topography spectrum encompasses typical variants used in bearing applications. So on the one hand, we had a linear flat crowned counterface, and on the other hand, we used concentrical grinding to produce the topography on the right side on that slide. Both surface finishing methods generate typical anisotropic surfaces, and we see that. So we have a clear orientation of the roughness peaks and valleys. The tribological tests were operated at one constant PV combination. So the contact pressure was round about 11.3 MPa in combination with continuous sliding speed of 0.1 meters per second. The lubrication state was dry, and the samples were decreased using a wet chemical cleaning process before we run the test. So on this slide, we see the first outcomes. So this slide shows you the exemplary friction wear curves of a polymer composite as a function of sliding distance. The friction is colored in orange, and the wear signal is red. So looking at the behavior of the material, it is obvious that this material shows two typical phases in friction and wear. So in most tests, the contact starts with a higher friction, which declines with progress in covered sliding distance until a steady state phase is reached. We can also call this phase the operational phase. This operational phase remains during the entire test duration. The wear characteristic can also be divided in two stages. The first phase is characterized by a higher wear curve slope. The wear rate decreases until the operational performing window is reached. During this phase, we find a linear wear characteristic for the wear curve. This slide shows the typical outcomes in friction and wear for a multi-layer material. Normally, these materials show typical friction wear phases during their wear life. So they often start with a low friction level, which can be attributed to an initial friction with a high content of PTFE. The duration of this transient phase strongly varies experiment to experiment. So both the variation in polymer overlay thickness in combination with the variances in counterface topography are two dominating factors for this phase. After this short initial period, the friction characteristic changes. So we see a clear increase in friction. This is caused through a structural alteration at the interface of both contacting surfaces. So during the first sliding meters, the PTFE-based overlay wears and is partly transferred onto the counter surface, resulting in an exposure of the subjacent bronze structure. So the bronze structure is now directly contributing to the sliding process, resulting in a PTFE lubricated bronze steel contact, which now responds with a higher friction. This phase is often followed by a fluctuating friction characteristic, and we can explain this fluctuation in friction by an ongoing running-in process, including the establishment of a bronze PTFE containing transfer film. Usually after that, we have a steady-state friction phase. Again, we can also call this the operational performing window of this material. And with progress in covered sliding distance, we see a clear change again in the friction characteristic. On the one hand, we see an increase in friction, and on the other hand, we see an unstable friction characteristic. So both are indicators that the system starts to enter its end of useful life. And the end of useful life is normally expressed through an escalating friction development. So you can see this on the right side of the graph. When we look at wear, we also see that we can also divide the wear in these four sections. So the running in wear of the system is normally a few microns. The variation in running in wear is often associated with the variation in overlay thickness. The running in wear is normally high. So over the time, we see a stabilization of the wear until we reach the operational performance window. And this stabilization of the wear can be explained that the bronze structure is coming in touch with the counterface, and the bronze structure, as already explained, is a really robust structure. During the operational performance phase, we have a low wear rate. Enter phase of end of useful life is normally accompanied with a moderate increase in wear. And at the end of useful life phase, we normally see an escalating wear development. So this shows you the wear performance of a polymer composite as a function of the counterface topography. It is clearly visible that the counterface topography is a dominating factor when experiencing high polymer wear. High wear of a polymer is often accompanied with a shorter life cycle and thus critical for the application. So the experiment showed that wear rates were measured in the range of 2 orders of magnitude. So what are the impact factors? So we measured 2 to 4 times higher wear when the polymer surface was stressed with a linear ground counter surface. For this counter surface, the polymer pin is stressed twice in roughness orientation and twice against the roughness orientation. And stressing against the roughness orientation is seen as the origin for high wear because we induce a lot of abrasive interactions. Another general trend is visible that higher wear at higher roughness heights. So this can also be explained by the amount of abrasive-induced wear actions. So the rougher the surface, the counter surface, the more abrasive interactions we have. In one of the introduction slides, we explained that polymer composites need to form a protective polymer film on the counterface to reduce its wear actions. So another hypothesis could be that rough surfaces just prevent the formation of a protective film, and the missing transfer film would explain the immense increase in wear at higher roughness heights. This slide shows the impact of the counterface topography on the wear performance of a multilayer material. It is obvious that the multilayer material reacts less sensitive on topography changes. The impact of the roughness height is also less pronounced, and the wear rates are comparable for both linear crowned and for a linear crown shaft and a concentrical crowned shaft. How can we explain that this material is just less sensitive to a topography change? In one of the slides, I explained that this material has a multi-layer architecture. We know that the top layer wears during the first sliding meters. This leads to an exposure of the underlying prone structure. And we know that this prone structure is very robust and has a very high wear resistance. And further, this robustness helps potentially to initially smooth the steel counterface in making it just less aggressive. We also know that these material concepts form a pretty stable and robust transfer film. And we know that such high quality transfer films help to effectively protect the bearing surface from damage by the attacking counterface. The results showed that smooth counter surfaces led to low polymer wear. One of the hypotheses we had is that low to medium rough surfaces promote the establishment of a protective transfer film. Such a film reduces the wear actions, which then lead to low wear. Looking on the right side, we see the wear readout of the experiment. We see that a smooth counterface leads to low wear during the operational performance phase. And again, we can explain this to a formation of a transfer film. And we see this formation of the transfer film in the SEM image below the graph. So the dark areas of this image is the transferred polymer on the steel surface, and the light areas of this image is the initial steel counter surface. Despite that the transfer film incoherently masks the counterface, it reduces the abrasive aggressivity of the counterface, leading to an improved wear performance. We also investigated the chemistry behind the transfer film. For us, it's always important what part or which part of the polymer transfers to the counterface. And we did some EDX analysis to get information about that. So what we see here is that we have two developed iron peaks and one big oxygen peak. And this explains what we see in the SEM, that the transfer film poorly masks the steel counterface. So these are the information of the steel counterface. What we also see is that we have a well-pronounced carbon peak, and we also have a likely fluorine peak, which is the left shoulder peak of the FE, which give a hint that the transfer film is predominantly composed of the matrix polymer with a contribution of PTFE. So previous results showed also that rough surfaces lead to enormous increase in system wear. So an increase in roughness heights can lead to an increase in abrasive-induced wear, especially when a softer material slides against a harder and rough counterface. Abrasive-induced wear is seen as a critical wear mode for polymer-based materials. We also speculated that a rise in wear is a result of a missing or an insufficiently formed transfer film. So to corroborate these statements, scanning electron microscopy was applied as before. And what we see here is on the right image of the SEM image that we don't have any transfer film. The only thing we can see here is that we have polymer-based wear particles not forming a transfer film. So this surface is still aggressive in terms of abrasive-induced wear actions. So we can explain the higher wear based on a missing transfer film. On this slide, I would like to show you the transfer film investigations we did on the multi-layer material. The SEM image of the counterface shows a well-developed transfer film. So the transfer film continuously covers the counterface, decreasing all the initial grinding marks. So we can't see any grinding marks they were present before. So only minor areas of the original metallic surface are still present. So these are the light areas. This covering of the protruding roughness peaks effectively reduces the abrasive wear actions into low wear. We also investigated the chemistry behind the transfer film. And what we see here is that we have an abundance of the following elements. So we see CO, Fe, F, Cu, Sn, and many more. So this is an indicator that the low peak of Fe is an indicator that the transfer film is really covering the whole surface. And we also see the other elements, which is coming from the PDFE, bearing liner, and the bronze structure. So the transfer film is composed of the bearing liner plus bronze. So now I come to the scientific conclusion of this talk. So a change in wear performance can often be explained by a change of the acting dominating wear mechanism in the contact. We found out that polymer-based materials can react very sensitive on a topography change of the attacking counterface. Abrasive wear actions are seen as a critical wear mode for polymeric materials. We also know, or we also have seen that transfer films are important for optimal sliding because they protect the bearing surface from aggressive wear actions of the counterface. To conclude on this, I think the presentation showed one important thing. So even a small change of a tribological system can lead to a massive change of the, even if it's only a change of a few micrometers, which is the topography. So what are the key takeaways of this webinar? So when applying tribology, it helps to identify critical factors of an application, including all the tribological subsystems. It helps to identify solutions to improve the system and the application. However, when we ignore tribology, it can be devastating for the tribological contact and thus for the whole application. So whether you look for cost savings, longer life cycles, improved performance, rate reduction, or maybe something completely new, we think that GGB can support you to find the optimal solution for your needs and your application. So the earlier we collaborate and share ideas and possibilities, the sooner we can help you to realize your objectives. We have a big group of local application engineers and a huge team of material designers and tribologists. So we provide an excellent technical resource you can collaborate with. So thank you very much for your attention, and I think the talk is now open for discussion.
Okay, well, thank you so much, Marco, and thank you, Andreas. Like you had mentioned, we're now going to open it up for questions. So the first we have coming in is we are going to start with how many different test rigs are available at GGB?
At the moment, we do have more than 40 active test rigs available at GGB. So we use them to describe the performance of our products or do some fundamental research works we do like this one. We do have 3 different testing categories. So we have simple model testers, which was also the basic for this investigation. And we also have simulation and component testers.
And Marco, is it possible to customize available test rigs?
Yes, we do have the possibility to tailor our test setup to the needs of an application. We call this customer or application-related testing. We know that friction and wear are system properties, and we achieve a much better transferability of friction wear results when adapting the system to simulate the real application. So yes, we can do that.
Okay, and I want to move on to some material questions here. Why is a multi-layer material more robust than a polymer?
That is a pretty good question. It depends on which kind of multi-layer system we use. We do have two classical systems. So one system with a thin overlay and one system with a thick polymer overlay. In this research project, we investigated the thin variant. So the system with a thick overlay reacts similar to a polymer composite because they were designed that the polymer overlay is always in contact with the counter surface. The thin overlay system, however, works differently. So the thin overlay is normally removed, leading to an exposure of the underlying bronze structure. And as already stated, this bronze structure is really robust against wear actions. And that is how we can explain that multi-layer material is more robust compared to a polymer-based material.
Interesting. And Marco, how robust is a transfer film?
A transfer film is a really tricky thing. So we see the transfer film also as a response of a tribological system. And therefore, its quality is normally affected by a vast spectrum of different impact factors. We know that a high-quality transfer film is a robust and thin layer that can effectively protect the bearing surface from further damage. Following microstructural features can be found for a good transfer film. Normally, when we have a thin, a well-covering, a highly orientated, and a well-adhering transfer film, normally we can say that we then have a robust transfer film. So it's a bit a tricky question because we can't give a clear answer because it's a response of a tribological system.
I see. Okay, well, so we still have time for a few more questions, so I'm going to keep moving along. So the next one is, does the counterface material also influence the performance of a Tribo system?
Yes, so it's also a pretty important part of a tribological system, not only looking at the topography, also the material itself can have an immense impact on the performance of a tribological contact. This directly depends on the material combination. So we can combine materials that have a good function together, so they work pretty well together, but when we choose that wrong, maybe that is a wrong combination which leads to direct failure of the contact. For example, when we have an adhesive failure of the contact, because both material work too good. So not too good. Both materials have a good solubility, so that leads to an adhesive failure of the contact. So that could also be critical. So again, thinking about the material pairing is also a pretty interesting and important thing about tribological contact. So as for the topography, when you do it right, it can last for a very long time. But if you do it wrong, it could lead to a direct failure of the contact.
Okay, we're going to keep moving along. A lot of great questions coming in, so we're going to get to as many as we possibly can. So the next we have, what kind of application is using the polymer compound? So where is that being used?
One typical application is for example, the automotive section, but that they can be used everywhere. So the only thing we might have limiting them in application is maybe the sensitivity to temperature, but normally we can use them elsewhere. So we have also a freedom in shape when we use the polymers. So it's not easy to say. It could be really everything. It's not so easy. But automotive is a good example where we use the EP range of the products.
Okay, so the next question I had for you, Marco, is somebody asked, why not directly apply polymer coating on the counter surface?
That is a pretty good question. We do have this technology in-house that we use, or that we modify the counter surface to our needs, that we always know what is the counter surface, and here we also use polymer-based coating systems. Yeah, that is true, and that works, yes.
Okay, so the next question is, does tribological theories apply to deformable surfaces and wiping, such as the wiping motion of a sponge over a surface?
I'm not sure if I understood the question correctly.
Sure. I think for the person that asked that question, at the end of the Q&A session, I'm going to provide everybody with links so they can, you can do follow-up and you can answer that one. So maybe we can come back to that after the webinar for the person that asked that. But I'll skip on to the next question for you. I think it's a little more straightforward. So how does temperature affect transfer film?
That is a good question. I would say similar to a polymer, because normally it's a polymer-based transfer film, and we know that polymer reacts very sensitive on temperatures because they change mechanical properties when they get heated up or cooled down. So that also applies to a transfer film because it's polymer-based. Yes. So it is affected by the temperature, yes. And if the temperature is too high,
Go ahead.
Okay, so if the temperature is high, maybe the transfer film becomes unstable, and then it gets worn by the polymer itself. But we also have seen that we might have a re-establishment of the transfer film again when the temperature comes down. So yes, it is affected by the temperature.
Okay, well, once again, Marco, thank you so much today, Andreas. I just want to remind everybody that if you have any additional questions or you want further clarification on any of the questions, you can refer to the speaker bio box, which contains contact information for Andreas, Marco, or myself. And lastly, of course, I want to thank everyone for attending this webinar from Design World. This presentation will be emailed to everyone later today and will also be available at designworldonline.com.